Okay, we are now on section 5 of chapter 5. I started my discussion yesterday for some for some of these types of convergence. So, as a review, we have three types of convergence. The first one, we have convergence in probability, or sometimes we call it as convergence in measure. The second one, we have almost sure convergence, or we may say also convergence in probability one. Uh, Let me check first. No, we call that convergence with probability one. But in mathematics, sometimes it is called as convergence almost everywhere. And then the last type of convergence, we have convergence in distribution. So for the first type of convergence, convergence in probability, we have here a definition as well as the definition for the other types of convergence. But I just want to emphasize that in this particular section of chapter 5, we want what we want is to be able to look at the behavior of our sample mean as n approaches to infinity. Itong part na to, no? We want to look at the behavior of the sample mean as n approaches to infinity. So for the first definition, we have here convergence in probability. What happened? Naghang? Can you hear me?
Sorry.
Pero hindi nagmo-move yung uh, slides. Andun na. Okay. So for the definition of convergence in probability, we have a sequence of random variables, x sub 1, x sub 2, and so on and so forth. It converges in probability to a random variable x, if for every positive epsilon, however small, the limit of the probability of the absolute difference of x sub n minus x greater than or equal to epsilon as n approaches to infinity will be equal to 0. Or equivalently, we have the limit of the probability of the absolute difference of x sub n minus x less than epsilon as n approaches to infinity will be equal to 1. Oh no. Excuse me for a while. What happened? Okay, I'm going to rejoin first. No connection for my iPad. One moment, please. Nawala yung connection ng iPad. Okay, so let me continue now. We have a sequence of random variables, x sub 1, x sub 2, and so on and so forth. It converges in probability to a random variable x. If for every positive epsilon, however small, then we have this limit, no? The limit of the probability of the absolute difference of x sub n minus x greater than or equal to epsilon as n approaches to infinity will be equal to 0, or equivalently, we have the limit of the probability that the absolute difference of x sub n minus x but less than epsilon as n approaches to infinity will be equal to 1. Okay, since we want to look at the behavior of our sample mean uh, as n approaches to infinity, so these random variables here, these random variables here can be replaced by the sample means. So we have a sequence of the sample means, x sub 1 bar, x sub 2 bar, and so on and so forth, and it converges to a probability to a random variable x. At this time, we may consider this random variable x here, it converges to a constant. No? Uh, in our case, we replace it by a constant mu. And that is being illustrated in this theorem 5.5.2. So we have an IID random sample. So for this IID random sample, we could we could derive a sequence of the sample means. Say we have here x sub 1 bar, x sub 2 bar, x sub 3 bar, and so on and so forth. That is why in the definition, we just replace the sequence of random variables x sub 1, x sub 2, and so on and so forth by a sequence of sample means x sub 1 bar, x sub 2 bar, x sub 3 bar, and so on and so forth. And then we replace the x sub n in our definition by the x sub n bar. Ito, makikita natin, x sub n bar. And then the limiting random variable x, we just replace it by the constant u here. And then since it is less than the positive epsilon, as n approaches to infinity will be equal to 1. And we say here, no, that would imply that the sample variance, rather the sample mean x sub n bar converges in probability to the population mean mu. And in notation, we have this form. X sub n bar converges to the population mean mu in probability as n approaches to infinity. To prove this theorem, we use the Chebyshev's inequality, and the proof is quite short. We have that. The weak law of large numbers actually actually implies a property, what we call the consistency property. Okay, so we have a sequence. We have the same quantity here, sample quantity. So we have a sequence of sample means. The sample means it converges to the population mean mu. And this is known as the consistency property. And in example 5.5.3, we have also the consistency of the sample variance S sub no S square, the sample variance, or S sub n square. And this consistency of the sample variance S sub n square uh, is satisfied if we're going to assume, if we're going to assume that the variance of the sample variance S sub n square, ito, if we assume that the variance of the sample variance S sub n square will approach to 0 as n approaches to infinity. Okay, so yan yung sinasabi dito sa example natin. But if we do not have that assumption, then we will not attain the consistency of our sample variance S square. Okay, so again, we have this theorem 5.5.4. If we have a sequence of random variables that converges in probability to a random variable x, x here is our limiting the limiting random variable. And then if we have a continuous function h, then a sequence of h of x1 or this random variable x h of x1, h of x2 will converge in probability also to a function h of x. Hence, we were able to uh, verify also the consistency of the sample standard deviation S. Again, this will happen if we have the assumption that the variance of our sample variance S sub n square, ito pa rin, no? Uh, will approach to zero as n approaches to infinity. Okay, so next we have the almost sure convergence. We have a sequence of random variables, x sub 1, x sub 2, and so on and so forth. It converges almost surely to a random variable x. So this x here is the limiting random variable. If for every positive epsilon, however small, magkaiba na ngayon yung form. Nagsimula tayo sa probability. So the probability that the limit of the absolute difference of x sub n minus x as n approaches to infinity, less than epsilon as n approaches to infinity, will be equal to 1. Again, let me remind you that our goal here is to be able to determine the property of the sample mean x sub n bar as n approaches to infinity. So in other words, we can now have a sequence of the sample means. So in this definition, 5.5.6, we simply replace this sequence of random variables by a sequence of the sample means. And then the limiting random variable x here, we replace it by a constant, the constant population mean mu. Mamaya ko pa yung i-discuss, no? Yung sinasabi nating strong law of large numbers. Okay? We have now a sequence of sample means, and then the limiting constant would be mu. But let me uh, discuss, or let me have a review first on this particular example. Example 5.5.7. So this is an example of almost sure convergence, not just an illustration to our definition. By the way, for the almost sure convergence, ang sinasabi nga dito sa almost sure convergence natin dito, no? It says here that definition 5.5.6 states that the random variable or the sequence of random variable x sub n converges to x almost surely if the function, if the function x sub n of s converges to x of s for all s in our sample space s, except perhaps for an s element of n, where n here is a subset of s in which the probability of n is equal to 0. The x sub n of s here converge to x of s here refers actually to the pointwise convergence of our sequence of random variables. That is for all s in the sample space big S, except perhaps for an S in our subset n of the sample space S, in which the probability of n here will be equal to 0. Okay, we have the pointwise convergence in this definition. I stop actually in this example. So we let the sample space S here be the closed interval 0 to 1. And then this is our sequence of random variables denoted by this. X sub n of s, s plus s to the n. And our limiting random variable, we have x of s, which is equal to s. For every, take note, for every s in the close open interval 0 to 1, in which 1 is not included. No, the right endpoint is not included because our sample space is the close interval 0 to 1. So if we choose S here, an element of the close open interval 0 to 1, we can see that our sequence of random variables x sub n of s, ito ngayon, no? X sub n of s, this sequence, x sub n of s, as n approaches to infinity, s of n approaches to 0, so at x n of s approaches to s. And this s is actually equal to our limiting, no? The value of our limiting random variable at s. So we have a pointwise convergence. No? The sequence of our random variable, it converges pointwise to our limiting random variable x of s. That is for s in the close open interval 0 to 1. Since our sample space is the closed interval 0 to 1, then we have an element, no, s, which is equal to 1 here in our subset big N, no? In our subset big N here of S, in which the probability of N is equal to 0. We can see here that if S is equal to 1, obviously, it implies that the sequence of random variables here, x sub n of 1, does not converge to the value of our limiting random variable x sub 1. Kasi magkaiba sila. Ito siya yung value ng x sub n of 1. That is for all n. No? That's for all n. But x of 1 is just equal to 1. So wala siyang, it does not converge to x of 1. So yung almost sure convergence, sinasabi dito, there is a pointwise convergence, no, to our limiting random variable. But for some subset in our sample spaces in which the probability of that subset is equal to 0, then the sequence of random variables does not converge on the limiting random variable. That is why the definition is just almost sure convergence. Kung sa mathematics pa, almost everywhere except only on a set in which in which the measure of that set is equal to 0. Kasi sa math, measure yung probability. The measure of that set is equal to 0. Okay, so I hope na nakuha niyo yung concept ng almost sure convergence. So let's have an example in which we have convergence in probability but not almost surely. Okay, for this. So consider our example now, in which we have our sample space S to be the closed interval 0 to 1 with a uniform probability distribution. Then we define our sequence x sub 1, x sub 2, and so on and so forth as follows. So kung x sub 1 natin of S is S plus the indicator function of S on the closed interval 0 to 1. And then x sub 2 of S is equal to S, ito no, S plus the indicator function of S on the closed interval 0 to 1/2. And then x sub 3 of S, S plus the indicator function of S on the closed interval 1/2 to 1. So yung sa x sub 4, ganun. So in other words, we divide the interval 0 to 1 into 3 parts. So 0 to 1/3, 1/3 to 2/3, and then 2/3 to 1. So ano kaya yung x sub 7 of S? Can you guess? Pwede daw i-try yung guess. Ano yung x sub 7 of S? That kasi yan. Pero just want to ask you if you can guess what is x sub 7 of S. Anybody? Who would like to try? Christine? Are you there? Naba mo karon din ha o wala? Tingog daw mo.
Nanaara, sir.
Anara di ay. Sige daw, sa mga next sub 7 of S, we have S plus what? The indicator function of S on the interval what? 0 to 1/4. Yung una, you divide it into two parts. So 0 to 1/2, 1/2 to 1. The next, we divide the interval 0 to 1 by three parts. 0 to 1/3, 1/3 to 2/3, 2/3 to 1. So next, we're going to divide the interval 0 to 1 into four parts. So 0 to 1/4. Next, x sub 8 of S would be S plus the indicator function 1/4 to 1/2. Then 1/2 to 3/4, then 3/4 to 1. Okay? So it says here, if we let the limiting random variable x of S will just be equal to S. It is straightforward to see that x sub n, this sequence of random variable x sub n, converges to x in probability. Says here, it is straightforward to see. Madali lang daw masyado. Pero paano natin ipapakita that the sequence converges to x in probability? So we're going to use the definition. So what's the definition? As n approaches to infinity, what do we have? In the convergence in probability, we have the probability that the absolute difference x sub n minus x, if it is less than epsilon, unsa atong pakita na ato ani? Kung if it is less than epsilon, this probability should be what? As n approaches to infinity, we're going to show that this probability would approach to 1. Okay, that's correct. Now, it will approach to 1. So, evaluate muna natin ano tong probability of this absolute difference, x sub n minus x less than epsilon. So, this is equal to the probability. Pwede natin siya ma-express as an event. Kung event siya, it would be the probability of the set of all S element in our sample space, a big S, such that the absolute difference x sub n of S minus x of S here less than epsilon. Okay, we have that. But as n approaches to infinity, this will approach to what? As n approaches to infinity, itong part na to, di ba supposedly, kung ang difference niyan, kung titingnan natin yung difference niya, dito ko lang isulat ha, yung x sub n of s here minus x of s, kung for a specific for a specific n, no? N natin, sabihin na natin, meron tayong s minus an indicator function, hindi natin alam yung kuha natin dyan, and then minus s, plus pala yan. So ang maiiwan is actually an indicator function on this particular close interval. Okay? On this particular close interval. But if we're going to have, if we're going to take n here, if we're going to take n here to be. So kung no, if we're going to take n here to approach to infinity, the value of this absolute difference, are you with me? If we take n here to approach to infinity, the value of this absolute difference of x sub n of s minus x of s will be 0. Okay? Will approach to 0 as n approaches to infinity. Diba? Say for example, sabihin na natin yung interval natin na 0 to 1, we divide it into 1,000 times lang. When n is equal to 1,000, say 1,000. So kung yung s mo dun, no, yung s mo dun, sabihin natin na ang value ng s natin, sabihin natin ang value ng s is 0.99. So yung 0.99, so yung 0.99 nasa interval siguro siya, sabihin natin nasa interval siya na nasa dulo na ng ika 99th 99th no, yung part, as we're going to divide the 0 to 1 into say 1,000 parts. Nasa ika 1,000 parts na siya yung value natin ng s. But most of the rest, it will be equal to 0. Kasi kung itong s na to, parang ganun yun, no? So itong s na to, kung nandito siya sa element dito na close interval, 1 yung value. So ibig sabihin yung absolute difference natin ng x sub n of s minus x sub s will be equal to 1. But most of the time, the value of that absolute difference will be equal to 0. That is why if we're going to approach n, to infinity, then the value of this absolute difference x sub n of s minus x of s will be equal to 0. Tama po ba? I hope naintindihan nyo. Yung sabi ko kanina, kung meron tayong 1,000 parts, out sa 1,000 parts, isa lang sa 1,000 parts, magiging 1 lang yung value nito. Kasi indicator function yan siya. Yung s na sa ganung interval. Pero the rest will be 0. Yung indicator function will be 0. That is why, as I have said, 1,000 lang yan. But if we're going to approach n to infinity, then this value, yung value ng ating absolute difference will approach to 0. Did you get my point? Okay, so itong set na to will just be equal to the probability of S. So parang lahat ng mga element ng S na yan, it will approach to 0. So the probability of S is equal to 1. And clearly, this approaches to 1. It approaches to 1. Yeah. Pwede na lang natin sabihin ganun na lang. Yung probability ng S, alam natin na equal to 1 yan siya, and this approaches to 1 as n approaches to infinity. The probability of the sample space is equal to 1, and we know that when n approaches to infinity, the probability of that will be equal to 1. So we have a pointwise convergence. X sub n converges to x in probability. Converges to x in probability. Okay, ganun yung ating So x sub n, therefore x sub n converges to x in probability. Okay, according to this example, we have convergence in probability. What about Why is it it's not almost sure convergence? So for every s, the value, no, for every s, the value of x sub n of s alternates between the values of s and s plus 1. Ganun lang. Ganun lang. Kasi ito, this refers to our indicator function. Pag yung element ng s, wala siya sa interval, that would be 0. Kaya ito yan siya, s plus 0. Ito siya, s plus 0. Pag wala siya sa interval. Pero pag yung s, the indicator function of s, nasa close interval, and that would be equal to 1 here. So, ang value niya, between s to s plus 1. So, say for example, if we say s here to be equal to 3, 8, 3, 8 natin yan. So, what is x sub 1 of s? X sub 1 of s is s plus 0 to 1. So, yung 3, 8 nasa interval 0 to 1. So, we have 1 plus 3, 8. So, we have here 3, 8. X sub 2 of 3, 8. X sub 2 of 3, 8. Yung 3, 8 nasa 0 to 1 half na interval. So, 1 yung indicator function. So, 1 plus 3, 8 still equal to 3, 8. Yan. What about sa x sub 3 of 3, 8? Yung x sub 3 of 3, 8, ang 3, 8 kasi mas less than siya sa 1 half. So, itong indicator function natin dito, itong part na to, yung indicator function natin dito, that will be 0. So, s lang siya. So, 3, 8 siya. Kaya ito ang answer natin, 3, 8. X sub 4 of 3, 8, 3, 8, and then so on and so forth. So, the implication of this, that our sequence of random variable does not converge. It does not converge to our limiting random variable x. Okay? Since what? Since the value of our x sub n has two possible answers. Ito, x sub n alternates. Since x sub n of s could either be 3, 8 or 1 and 3, 8. It does not converge pointwise. Okay, it does not converge. The sequence of x sub n does not converge pointwise to our limiting random variable x. Okay, so it says here, no pointwise convergence occurs for this sequence. So not almost surely convergence. Okay, we have here a remark that convergence almost surely implies convergence in probability. Okay, I hope you get this one. Convergence almost surely implies convergence in probability. But the converse is not necessarily true based on our example. Yan ang example dito na convergence in probability. Na kanitong example natin above. Example 5.5.8, convergence in probability, but it is not almost sure convergence. But if we have an almost sure convergence, it would imply that we have a convergence in probability. So, as I have said, in our definition, we have a almost sure convergence. We have a sequence of random variables, x sub 1, x sub 2, and so on, that converges to a limiting random variable x sub n. And then the limit, or rather the probability of the limit of the absolute difference of x sub n minus x, if it is less than epsilon, as n approaches to infinity, it will be equal to 1. So this time, instead of having a sequence, as in our definition, we just replace the sequence of random variables here by a sequence of sample means. So, ibig sabihin, kung meron tayo dito, we have this vector, x sub 1, x sub 2, and so on and so forth. No? Meron tayong sequence na yan. Then we can, this would imply that we can derive a sequence of sample means. So, ano yung sequence of sample means natin? X sub 1 bar. The x sub 1 bar is actually equal to x sub 1. Then we have another x sub 2 bar. So that's the summation of x sub I from 1 up to n over n, and so on and so forth. So meron tayong sequence of sample means. And our limiting random variable, we just replace it by a constant u. So based on the almost sure convergence definition, we have here now the limit of the probability of the limit of the absolute difference of the sample means minus the sample mean minus the population mean less than epsilon as n approaches to infinity will be equal to 1. So x sub n converges almost surely to 1. So ganun yung notation natin. X sub n bar, it converges almost surely AS to mu as our sample size n approaches to infinity. Again, ang property ng ating sample mean, the property of our sample mean, it approaches almost surely to the population mean mu as n approaches to infinity, based on the strong law of large numbers as well as on the weak law of large numbers. We call it as a strong law of large numbers because we use the almost sure convergence in this theorem, which is actually a stronger type of convergence compared to convergence in probability. Okay, we have a remark here again. Both the weak and the strong law of large numbers have an assumption that we have a finite variance. Kita naman natin dyan, variance of x sub I is equal to sigma square and it is finite. So we have an assumption of a finite variance. Okay, this assumption is true and desirable in most applications. In fact, a stronger assumption, it is in fact a stronger assumption than is needed. Sobra lang ba? In other words, we can the weak law and the strong law of large numbers can still hold without the assumption that the variance of our the variance or without the assumption of a finite variance. So the only condition needed is that the first absolute moment will just be finite. Okay, that's for convergence, almost sure convergence. Let's proceed now to the third type of convergence. Okay, we have already encountered the idea of convergence in distribution in chapter 2 when we deal on the properties of the moment generating functions and how their convergence implies convergence in distribution. We see that in theorem 2.3.12. In other words, we have what we call convergence of moment generating functions. Sabihin natin, based on our theorem, we have convergence in moment generating functions, and this implies that we have convergence in distribution. Yung distribution natin sinasabi dyan, convergence in the CDFs, in the cumulative distribution function, in big F. Okay, we have No? If you're going to look at this theorem 2.3.12, we have discussed that in chapter 2. Okay, so we have here now, uh, we're going to discuss in detail this type of convergence. So a sequence of random variables, x sub 1, x sub 2, converges in distribution to a random variable x if the limit of this CDF, it's a CDF, the limit of this cumulative distribution function, big F sub x of n evaluated at x as n approaches to infinity, will be equal to this CDF, big F of x evaluated at x. At all points x where the CDF is continuous. Some important notes that you're going to remember. We have here the definition of the CDF. It is equal to the probability that our random variable x is less than or equal to small x. That is for all real number x. Okay? So if we have a sequence of random variables here that converges in distribution to a random variable x if the limit. By the way, sinasabi dyan sa ating definition na ang mga random variables converges in distribution to a random variable x. But if you want to read it carefully, it is it is not the random variables that converges. It is actually the CDF, the CDF of these random variables converges to the CDF of the limiting random variable x. So, ibig sabihin yan, kung meron kang x sub 1 dito na random variable, meron siyang corresponding na CDF f of x sub 1. Itong random variable na x sub 2, meron din siyang corresponding CDF f of x sub 2, random variable nila. And then so on and so forth. So we actually obtain, we have a sequence of CDFs. That is why we have the limit here, the limit of CDFs. So convergence in CDF, limit of the CDF equal to the CDF of the limiting random variable. So we have now this notation here that our random variable x sub n converges in distribution to x if, okay, it says here, if the CDF converges at all points, as n approaches to infinity for all continuity point x. Or pwede din sabihin natin the probability that x sub n less than or equal to x here converges to the probability that x less than or equal to x here. As n approaches to infinity for all continuity point x. Okay, let's have an example to illustrate this definition, convergence in distribution. If x sub 1, x sub 2 are ID, uniform, 0, 1, and then we have here the maximum order stat, x sub quantity n. So let us examine if and to where this maximum order stat converges in distribution. So as n approaches to infinity, so we would expect, because it's a maximum order stat, we would expect that the maximum order stat will get to get close to 1, or would be must necessarily be less than 1, close to 1 but less than 1. Okay, let us recall the 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 joint, or rather the PDF for this random sample. We have here 1 over b minus 1, or 1. Okay, so which is x between 0 and 1. Oh, so simply it is equal to 1. So 1 na lang yan siya. And then yung CDF natin will be equal to x minus 1, x minus 0, 1 minus 0. So x lang tayo. That's the support. 0 to 1. Okay, so it says here now that the probability we have for any positive epsilon, however small, the probability that the absolute difference of this maximum order stat minus 1 greater than or equal to epsilon. So if it is greater than or equal to epsilon, so if as n approaches to infinity, malalaman natin yan that this would approach, to 0. It says here, no, as n approaches to infinity, it will approach to 0 in this case. So atin muna itong, okay, so we have this absolute value, absolute value. By definition of the absolute value, we could have the probability that we have x sub quantity n minus 1 to be greater than or equal to epsilon, or that's by definition of the absolute value, x sub n quantity n minus 1 to be less than or equal to the negative epsilon. So the next equality holds. Okay, we have the probability that x sub quantity n to be greater than or equal to 1 plus epsilon plus 1 minus epsilon. Oh no. Since the value, the maximum order stat will not exceed 1, sabi dyan, the probability that x sub n greater than or equal to 1 plus epsilon. We have an epsilon which is positive, however small, but the value of our order stat here will not exceed 1. Therefore, this probability will be equal to 0. So, ang maiiwan na lang yung second term. Okay, yung second term. And this would be equal to, we have here the probability that x sub quantity I less than or equal to 1 minus epsilon. This is for I 1 up to n. Okay, since we know that our x sub in here is the maximum of the x sub I from hindi pala yan siya order stat, sorry, kaya pala should be x sub I lang. Mabuti na lang na sinulat ko. Okay, 1 up to n. So the maximum of x sub I. So hindi siya order stat, no? X sub I lang siya. And then, since we know that we have a random sample, so mutually independent, so we can have the probability of what? Pwede naman yan, no? Bago muna siguro, sabihin na lang natin, x sub 1 less than or equal to 1 minus epsilon, x sub 2, 1 minus epsilon, and so on and so forth up to x sub n less than or equal to 1 minus epsilon. Okay, since we have a random sample, mutually independent, we can have now the probability of x sub, pwede lang siya tayo, x sub 1, 1 minus epsilon. And in this case, this is being raised to the power n. ID. Kung naman tayo, dumiretso naman tayo kagad. Si x sub 2 muna. Independence muna tayo. Probability, dot, sign the probability of x sub n Independence muna tayo, ha? And then, identically distributed. Kung identically distributed siya, then we have now the probability that we have x here. And this would be raised to the power. Ito, independence. By independence, ito pangalawa, identically distributed. Kasi random sample man tayo. Distributed. So if x now, alam natin yung x natin is uniformly distributed on 0 to 1. So ano to siya? Ano to? Itong part na to, diba parang expression na yan siya na, diba? Diba? Halos pareho yung expression, diba? So ano to? Kung ang x natin is, alam natin na ang x is uniformly distributed. Meron tayong x. X ang answer niyan. Kasi? So what should be our answer here? This answer would be equal to what? 1 minus epsilon raised to the power n. Raised to the power n. Kaya ito, satisfies the probability that itong part na to, ito yan siya. Equal now to 1 minus epsilon to the power n. Para klaro, no? X here has a uniform distribution. 0, 1. Kaya yung CDF niya, X lang. 0, 1. And then it says here, it goes to 0 as n approaches to infinity. So, ibig sabihin yan, patuloy tayo. This will approach to 0 as n approaches to infinity. In other words, we can verify. Pwede nyo ma-verify. You can verify now that the limit, no? Parang ganito yan siya. You can verify up, so clear, no? As n approaches to infinity here, 1 minus epsilon here, we can choose epsilon. We can verify this. We can choose epsilon here to be positive, however small, no? Positive, however small. So 1 minus an epsilon, that would be a value smaller than 1. But if you're going to raise that to n as n approaches to infinity, and clearly that will be equal to 0. Hindi ko na lang iikan yan, no? Klaro naman yan siya. This epsilon, we know that this epsilon is positive. We can choose however small. No, however small. Maliit masyado. So 1 minus epsilon is a value of less than 1. Okay, then it goes to 0. Then we're going to prove. Because this is, itong part na to, greater than or equal to epsilon dyan siya. So kailangan natin ma-check na the probability, we have to prove that the x sub n, no, the maximum order stat converges to 1 in probability. So we have here, uh, uh, yeah, because it's equal to 0. So however, if we take epsilon here to be equal to t over n, we have this, and this approaches to e to the t. Ang pang-verify nito, you're going to use your knowledge in calculus. Ito lang yung pag-verify natin. Verify that the limit of 1 minus t over n n approaches to 0, or rather, as n approaches to infinity, this would be equal to e to the negative t. Kung i-apply mo yung limit, you have this result, 1 to infinity. Obviously, that is an indeterminate form. Hence, you're going to apply what you have learned in calculus to be able to evaluate this limit. And the result of that is equal to e to the negative t. Okay, so we can now have the probability that we have n times this maximum order stat. It would be, okay, it would be less than or equal to n minus t. Yan. So this approaches to e to the negative t. So n approaches to infinity. And then we have the probability that we have n here. Pwede natin yan. Palitan natin yan. We have here 1 minus this maximum order stat. This would now greater than or equal to t. Okay? We transpose n on the other side. We factor out n. Pag-factor out natin n, pero meron tayong 1 minus x sub-quantity n. So, dapat na negative yun siyang negative 1, then positive x sub n. So, the sense of inequality is being reversed in this case. Again, this approaches to e to the negative t. Okay, now the probability of n times 1 minus this maximum order stat, if it is less than or equal to t, this would be equal to 1 minus the probability that n. Okay, so this implies, so this approaches to 1 minus e to the negative t. So notice, no, yan yung ng form natin. Ito na yung na express na natin. 1 minus e to the negative t. We have verified that one. So notice that this expression here, itong expression na to, CDF ito. This is the CDF. Diba, the probability that x is less than or equal to x, it's the CDF, big F of x. So ano to? Big F of what? N 1 minus x of n. And then evaluated at t. Yung part na yan. So we have a CDF, and the CDF, okay, our CDF now, the CDF now converges, because we have convergence here, convergence. It converges in distribution to an exponential 1 random variable. Okay? So the sequence of CDFs now converges to this CDF having an exponential 1 random variable. Any questions or clarifications? Based on our example, Convergence in probability will imply convergence in distribution. Now, based on this example. So we have that uh, illustration for our definition for convergence in distribution. Another remark, we have a sequence of random variables converging in distribution. It is really the CDF that converge, not the random variables. Okay, in this very fundamental way of convergence in distribution is quite different from convergence in probability or convergence almost surely. However, it is implied by the other two types of convergence. So, yung remark nagsasabi that if our random variable converges in probability to this random variable x, so this would implies that our random variable x converges in distribution to x. Also, if the random variable sequence of random variables x sub n converges almost surely to x, it also implies that our sequence of random variables x sub n will converge in distribution to x. Ano yung nalaman natin sa previous example natin? Convergence in almost sure, no? Convergence almost surely, or almost sure convergence implies a convergence in probability. But the other way around is not true. Now, convergence in probability does not necessarily imply convergence almost surely. Okay, so yun yung mga remarks natin. Theorem 5.5.12, we have here, if the sequence of random variables x sub 1, x sub 2 converges in probability to random, then sequence also converges in distribution to x. Yun yung sinabi ko kanina, no? The proof is actually an exercise in 5.40. Then convergence in distribution is also implied by almost sure convergence. So yun din. Almost sure convergence, it will imply. And then based on theorem 5.5.13 says here, a sequence of random variables x sub 1, x sub 2 convergence in probability to a constant u. If it's a constant u, then we have if and only if, okay, if and only if the sequence also converges in distribution to mu. Okay, so ito ang sinasabi niya. Yung kanina meron tayong limiting distribution, no? May limiting distribution tayo na x. Pero pag constant na yung limiting distribution natin, yung sequence, no, of random variables converges in probability to our constant u. Kung constant u siya, so ibig sabihin din yan na if and only if na meron tayong biconditional statement na ngayon, then our sequence of random variables will converge in distribution to u. Okay, so this is for when we have our limiting distribution to be a constant. In this case, the constant is the population mean mu. Take note, the constant should be the population mean mu. Should not be any other constant. It should be the constant population mean mu. So one of the application of this third type of convergence, which is convergence in distribution, we have what we call the central limit theorem. Okay, it says here, let x1, x2 be a sequence of IID random variables whose MGF exist in the neighborhood of 0. That is, the moment generating function exists for the absolute value of t less than h for some positive h. In other words, we have here, kunwari ito yung 0 natin. on the neighborhood of 0. So bear with my drawing. Say this is a circle, and then this point here is the center of the circle, which is the 0 value. And the radius of our circle, that is our h. That is our h. And the points t here, nandyan lang yan siya. Okay, we have a streak. We have a streak inequality. It should be less than h. So the points, ito yung mga points natin na t, will not fall on the circle kasi it should less than the radius of our circle. So the moment-unity function exists in the neighborhood of 0 here. So let the mean of xi is equal to mu, the variance of xi is equal to sigma square, which is positive. Okay, it's positive. And then we define the sample mean of the n observations, x sub n bar, and then we denote g sub n of x, denote the CDF of this random variable. Ito na yung random variable natin. We have here square root of n, and then times this fractional expression, x sub n bar minus mu divided by sigma. Then for any x in the set of real number, okay, so we have the limit of this CDF as n approaches to infinity would be equal to a CDF. Kasi yung sinasabi natin sa distribution in distribution, we have the limit of our CDFs will be equal to a CDF. Actually, this is a CDF of what? This is the CDF of what? CDF of a standard normal random variable. And usually we denote this by capital letter Z. In other words, we have this transformation. Meron tayong transformation na Z. Equal yan siya sa ano? The random variable, the sample mean, x sub n bar, minus the mean of the sample mean. Ano yung mean ng sample mean? Based on what we have learned in the previous sections, if we have an IID, we do not know the distribution of that. The mean of the sample mean is equal to the population mean, U. And then the variance of the sample mean is equal to sigma square. Divided by, i-divide natin ngayon by the standard deviation. So we have now the square root of the sample, or the square root now of the variance of our sample mean, which is equal to sigma square over n. That is why we have this result, no? Itong blue natin dito sa itaas. Yung g of n here denote the CDF of that. Okay. So, itong z natin ngayon, z sub n ito. No? Meron tayong z sub n yan. Yan yung z sub n natin. That's our transformation. So, this time, meron tayong sinasabi, meron tayong mga CDFs ng ating z sub n. So, ibig sabihin, meron tayong sequence of random variables, z sub 1, z sub 2, and so on and so forth. Yan yung sequence nating random variable. Then, according to this random variable na z sub 1, meron tayong CDF na g sub 1, okay, g sub 1. Ito, meron siyang g sub 2. Pwede naman yan may x tayo, no? And then so on and so forth. So we have this sequence sequence of CDFs. Okay, so we have here a sequence of CDFs. So itong central limit theorem is actually an illustration of the definition of convergence in distribution. We have the limit of our CDF approaches to a CDF. A stronger form of the central limit theorem here we have here, no? Let x sub 1, x sub 2 be a sequence of IID random variables with the mean x sub I is equal to mu. The variance is positive but finite. Okay? Finite. Yung kanina, it considers the MGF of our random variable. We define again the sample mean of the n observations. Then we have this let g sub n of x denote the CDF of this random variable. Okay, this random variable. Then for any real number x, then the limiting, the limiting distribution of this CDF g sub n of x as n approaches to infinity is still the standard normal distribution, having a storm. Okay, so ang sinasabi dito sa ating central limit theorem, we have a sequence of IID random variables. Not necessarily na ating random variables are normally distributed. At sinasabi lang natin na meron tayong IID, independent and identically distributed random variables. So we have this random variable here. Itong random variable here natin. Itong random variable na. We have that variable. Then the CDF, no? We have a sequence of this random variable. Then the CDF or the limiting CDF of this sequence of random variables guys, are you there? Wala yung signal ko.
Yes, sir.
No. Wala na ako, hindi naka-share na, no? Malit, konti na lang. Tapos na tayo. Rejoin ko muna. Oh no. What's the signal in my iPad? Kapit na tayo matapos na dahil masyado to. Wala pag ang signal. Internet connection. Okay, so let's have this. Yan na yan. Malapit na tayo. Okay. 2 pages na lang. We have this example, normal approximation to the negative binomial. Suppose we have x sub 1 up to x sub n are random sample from a negative binomial RP distribution. So recall that if we have x here having a negative, binomial. So we have here RP. So ibig sabihin itong X natin dito, this is the number. Pwede natin sabihin that is the number of failures before the art success. Before the art success. Okay, so the probability mass function for this, yan yun. Ito yung probability mass function niya. We have here R plus X minus 1 taken X at a time. Then we have here the probability of success raised to R, the probability of failure raised to X. So the support for this, 0, 1, and so on and so forth. Okay, and then we know that the mean of X here is equal to R. Then we have 1 minus P over P. And then the variance of X is equal to R 1 minus P over P square. Okay, so we have that. Yan yun, no? We have the mean, we have the mean. Okay, so based on our central limit theorem, first, note that ano yung mean ng sample mean natin? Hello guys, ano yung mean ng sample mean? We have we have a IID random sample from a negative binomial RP distribution. So what's the mean of the sample mean? Hello guys, anong mean ng sample mean? Lapit na tayo matapos. IID tayo, so ibig sabihin negative binomial RP siya. So ang mean ng sample mean must be equal to the population mean. Ano yung population mean natin? Yung population mean natin, yung mean ng ating random sample. So it is equal to, pareho lang, R 1 minus P over P. Ano naman yung variance ng ating sample mean? Ano yung variance ng sample mean? We have learned that in a previous section, it would be equal to the population variance divided by n. Ano yung population variance? R 1 minus P squared divided by, you divided this by n. Divided this by n. Therefore, based on the central limit theorem, the sample mean, ito yung ngayon, the sample mean minus the population mean, ito yung population mean natin, divided by the standard deviation of the standard deviation of the sample mean. So ano yung standard deviation ng sample mean? So kung sabihin natin standard deviation, STDV, ano yung standard deviation, ano notation natin doon? Square root na lang, no? Variance. So the square root, ito yung variance. That will be equal to this. We have the square root, okay, the square root of R 1 minus P over P square times square root of 1 minus N. Okay, so ito yung result natin here. This is now the standard deviation. And according to our central limit theorem, this has a standard normal distribution. So, ano yung advantage nito central limit theorem? Say for example, if we take R here to be equal to 10, and then the probability of success is equal to 1/2, and we simply have the sample size to be equal to 30, if we're going to compute for the probability that the sample mean is less than or equal to 11, less than or equal to 11, using the definition of using the distribution of a negative binomial distribution, then we have this. Yung x bar natin, less than or equal to 11. So that means we have here 1 over 30 summation of xi, I from 1 up to 30, less than or equal to 11. So the summation of xi, I from 1 up to 30, will be less than or equal to 330. Okay, that's the first equality here. Yung first equality natin. And then, the second equality, this is true because the summation of I here, x sub, sabihin na lang natin, sorry. Parang ito, no? Itong part na to. Is the summation of x sub I from 1 up to n, meron siyang binomial. This has a binomial NR-P distribution. Given that, no, if x sub I here, x sub I is as a negative binomial distribution na RP, ito lang RP, this implies na yung summation ng x sub I from 1 up to n, has a binomial NRP distribution. Okay? So, ibig sabihin, itong pala, itong part na to, itong summation of xi, I from 1 up to 30, meron itong distribution na, ibahin ko na lang, this one, meron siyang distribution na binomial NRP. So, ang n natin, ano yung n? Binomial n is 30. R, so 300. And then, okay, so we have this. Supposedly, less than, we have the probability. Okay? Kasi yung value ng ating, the value ng ating x dito is from 0 up to 330. So supposedly yung, ito siya, CDF sana to. CDF of a discrete distribution. Pero the probability that the summation of x sub I less than or equal to 330, no, 330, pwede siya express, no, as the probability of x sub 1 less than or equal to, no, the probability of x sub I having this distribution, and using the definition of probability, and then since less than or equal to x man yung sa CDF natin, but we're going to take the summation now for a specific x, 0 up to 330. Kaya ito yung second equality holds. And then if we're going to compute this, we have this value. It says here, this is a very difficult calculation. Note that the calculation is difficult even with the aid of a computer. It's because we have here the magnitudes of the factorials. So, meron tayong value. Mahirap masyadong makuha yan. So, to be able to solve this probability using the central limit theorem, it will give us this approximation. So, we have the probability that the sample mean is less than or equal to 11. Then by transformation, we have this transformation. We subtract 10 sa sample mean natin. Then we subtract 10 also on 11. Then we divide it also by square root of 20 over square root of 30. Then we have that. Because we know that the mean of x here, okay, the mean of x, we have r is 10, 1 minus 1 half, actually p is 1 half, divided by 1 half. So the mean of x here is equal to 10. And then the variance of x, based on our formula, we have 10 times 1 minus 1 half over 1 half square. Sorry. Over 1 half square. The answer is equal to 20. Okay, so the end value here is equal to 30. So square root of 30, then the square root of the variance of x, that we have here 20. Okay, so we take this as our standard normal random variable z, and then we can look at the standard normal table to compute this probability. So you have this value, or you can use the R software to compute this probability. Hence, we have this result using the central limit theorem. Okay, just a few minutes. An approximation tool that can be used in conjunction with the central limit theorem. We have what we call the Slutsky's theorem. So we have here the Slutsky's theorem. If x sub n approaches to x in distribution, y sub n approaches to a is a constant in probability, then the product y sub n, x sub n approaches to ax in distribution, and the sum x sub n and y sub n approaches to x plus a in distribution. Okay, I don't intend to give the proof for this theorem. So for the last example, before we're going to end, we have here the normal approximation with estimated variance. Okay, suppose that we have here this random variable approaches to a standard normal distribution, and say the value of sigma here is unknown. And as I have explained a while ago, in example 5.5.3, the sample variance S sub n square converges to the population variance sigma square. We have what we call here the consistency property. If we have that assumption, if the limit of the variance of the sample variance as n approaches to infinity is equal to 0. Okay, if we have this assumption, then we know that the sample variance S sub n square will converge in probability to the population variance sigma square. Alam natin yan sa example 5.5.3. Okay, so ito yung hahanapin natin ngayon. What would be the distribution of this random variable? And then according to exercise 5.32, it's an exercise. So ibig sabihin, kailangan isolve nyo pa yan. It's an exercise. Then we can show that this expression sigma over S sub n will converge in probability to 1. So kung totoo ito, by showing this exercise 5.32, then if we're going to use the Slutsky's theorem, itong random variable na to on the left-hand side of the equation can be expressed in this manner by, say, multiplying sigma over sigma. Okay, sigma over sigma. And then we can have this product of factors, of these two factors. And since we know that this, it approaches to standard normal 0 to 1, and then according to exercise 5.32, ito siya, it converges to 1 in probability. It converges to 1 in probability. Ito siya, it converges to n. Ito, it converges to n standard normal in distribution. So according to the Slutsky's theorem, kung ito converges in probability, ito converges in distribution, then this expression now, it converges to a distribution. Ito yung distribution niya. Standard normal, 0 to 1. So we are left to show this part. Itong part na to, Slutsky's lang naman yan, yung application. Ang kailangan natin papakita ngayon kung yung sigma over S sub n approaches to 1 in probability. How are you going to do that? If you're going to show this exercise 5.32. Okay, so you try to solve this. Baka lalabas ito sa exam. Yung exercise 5.32. Madali lang masyado yan, no? Yung part na yan. You just use one of the theorem. If we have a sequence of random variables, a function of this sequence of random variables will also converge to the function of the limiting random variable. So we can prove easily this exercise 5.32. Okay, so that's all for this afternoon. Actually, this is now the last meeting natin, lecture. So, magbibigay na lang ako sa inyo bukas o ngayong gabi. Kung magawa ko ngayong gabi, hindi ko nagawa kasi. So, I'm going to make the problem set tonight and I'm going to send it to you by tomorrow. And then our exam will be Wednesday next week, October 27. Before sa exam, masasauli ko na yung problem set niya, problem set number 1, and then the result of your first exam. Okay, so any questions or clarifications before we go? So yung discussion ngayong hapon is all about types of convergence, the 3 types of convergence and its corresponding application. Yung convergence in probability, yung concrete example niya is the weak law of large numbers. Yung almost sure convergence, yung concrete example niya is the strong law of large numbers. Yung convergence in distribution, the concrete example of that is the central limit theorem. Because of the fact that the goal of this section is actually knowing the properties, the properties of our sample mean as n approaches to infinity. Though we have solved some problems that does not involve the sample means. Para lang ma-illustrate yung definition natin. That ang focus is to be able to determine the properties of our sample mean as n approaches to infinity. Yung weak law of large numbers says there that the sample mean converges in probability to the population mean. Okay, knowing that we have a random sample. Strong law of large numbers, parang pareho pa rin, that the sample mean converges almost surely to the population mean. Pareho pa rin yung implication niya. In the central limit theorem, we do not have exactly the sample mean, pero we can still get the distribution of the sample. But it says there that the sample mean minus the population mean divided by the standard deviation of the sample mean, this will approach in distribution to a standard normal distribution. And then we have an example for that. Then we end up uh, with this theorem, what we call this Latsky's theorem. Okay, any questions or clarifications before we go? Anim na lang sila, oh. Ilan na ba tayo dito? Okay, so I think parang walang question. Kim, may question? Noli? LJ?
Sir.
Dina? Mary Jean? Shara? Okay, so we're done with our lecture. So exam na lang at saka problem set. Okay, so that's all for this afternoon and class dismissed. Bye everyone.
Thanks,
Okay, stop na the recording.
Philippines.